When dealing with a 1 horsepower or less 115 volts motor in a forced hot air heating, ventilation, and air conditioning system with multiple speeds, it's important to understand the wiring configuration, especially concerning the capacitor. The white lead coming out of the motor case alongside the black, blue, and red leads represents the common line. This common line should be connected to the incoming common wire, which is typically also white. The capacitor wires, often brown and brown with a white stripe, are situated on the opposite side of the motor case and are specifically for connecting to the capacitor. The solid white capacitor wire and the brown wire with a white stripe serve the same function. They are electrically equivalent, and either one can be used to connect to the common side of the capacitor. It is acceptable to connect either the solid white capacitor wire or the brown wire with a white stripe to the common side of the capacitor along with the incoming white wire. The remaining capacitor wire, which is typically brown, should then be connected to the other post of the capacitor. Consider the implications of different wiring configurations. If you were to disconnect the solid white lead and tape it off, and then connect only the brown wire with the white stripe to the common side of the capacitor along with the incoming white wire, the motor may still function, as these two wires are essentially interchangeable for the capacitor connection. However, it's generally recommended to follow the manufacturer's specified wiring configuration. If the solid white motor lead is connected to the incoming white wire, and the brown wire with a white stripe is connected to the capacitor common with the brown wire connected to the other capacitor post, this is likely the correct and recommended hookup. The brown wire with a white stripe is likely provided to simplify the connection to the capacitor, offering a dedicated wire for this purpose. The provided wiring setup is likely for a capacitor start-only type motor. This means the capacitor is only active during the motor's startup phase. Once the motor reaches its running speed, the capacitor is no longer actively involved in the circuit's operation. This is a common design for smaller motors where the capacitor provides a temporary boost to overcome initial inertia. Here's a recommended wiring configuration to ensure proper motor operation and capacitor function exclusively during startup. Firstly, connect the solid white motor lead to the incoming white wire. Secondly, connect the brown wire with a white stripe to the common side of the capacitor. Thirdly, connect the brown capacitor wire to the other post of the capacitor. This configuration aligns with the typical design of capacitor start motors, where the capacitor assists in starting and then is removed from the circuit. Now let's delve deeper into capacitor start motors. These motors use a capacitor to provide a starting torque. The capacitor is connected in series with an auxiliary winding, also known as the starting winding. This arrangement creates a phase shift between the current in the main winding and the current in the auxiliary winding, producing a rotating magnetic field that initiates the motor's rotation. Once the motor reaches a certain speed, a centrifugal switch, or other type of switch, disconnects the auxiliary winding and the capacitor from the circuit. At this point, the motor runs solely in the main winding. The key components of a capacitor start motor are firstly the main winding, which is the primary winding responsible for running the motor. Secondly, the auxiliary winding, which is used only during startup to provide the necessary torque. Thirdly, the capacitor, which provides a phase shift in the auxiliary winding to create a rotating magnetic field. Fourthly, a centrifugal switch or another type of switch which disconnects the auxiliary winding and capacitor when the motor reaches a certain speed. The capacitor used in these motors is typically a non-polarized electrolytic capacitor designed to withstand the high voltage surges that occur during starting. It is important to use the correct capacitor value, as an incorrect value can lead to starting problems or even damage to the motor. The voltage rating of the capacitor should also be appropriate for the motor's voltage. Capacitor start motors are commonly used in applications that require high starting torque, such as air compressors, refrigerators, and other appliances. They are relatively simple in design and are cost-effective, making them a popular choice for many applications. Now let's consider continuous capacitor motors, also known as capacitor run motors. Unlike capacitor start motors, continuous capacitor motors keep the capacitor in the circuit continuously while the motor is running. This is achieved by using a smaller capacitor value and a different winding configuration. The capacitor in a continuous capacitor motor serves two purposes. Firstly, it provides a starting torque similar to a capacitor start motor. Secondly, it improves the motor's running efficiency and power factor. By keeping the capacitor in the circuit, the motor's current and voltage waveforms are brought closer together, reducing losses and improving the overall efficiency. Continuous capacitor motors are typically used in applications where efficiency is important, such as fans, blowers, and pumps. They are more efficient than capacitor start motors, but they also tend to be more expensive. The key differences between capacitor start and continuous capacitor motors lie in firstly, the capacitor value, where capacitor start motors use a larger capacitor for high starting torque, while continuous capacitor motors use a smaller capacitor for both starting and running. Secondly, the capacitor connection, where capacitor start motors disconnect the capacitor after starting, while continuous capacitor motors keep the capacitor connected continuously. Thirdly, the efficiency, where continuous capacitor motors are more efficient than capacitor start motors due to the improved power factor. Fourthly, the application, where capacitor start motors are used in high starting torque applications, while continuous capacitor motors are used in applications where efficiency is important. When replacing a motor, it is crucial to ensure that the replacement motor is compatible with the existing system. This includes firstly, the voltage and frequency, where the motor should have the same voltage and frequency ratings as the original motor. Secondly, the horsepower, where the motor should have the same horsepower rating or slightly higher if needed. Thirdly, the speed, where the motor should have the same speed rating to ensure proper operation of the equipment it is driving. Fourthly, the mounting, where the motor should have the same mounting configuration to fit into the existing system. Fifthly, the wiring, where the motor should have the same wiring configuration or be adaptable to the existing wiring. The motor's nameplate provides valuable information about the motor's specifications, including the voltage, frequency, horsepower, speed, and current ratings. It is important to carefully review the nameplate information to ensure compatibility. When working with electrical systems, it is crucial to follow safety precautions to prevent electric shock and other hazards. Firstly, always disconnect power to the circuit before working on any electrical components. Secondly, use appropriate personal protective equipment such as insulated gloves and safety glasses. Thirdly, follow all applicable electrical codes and regulations. Fourthly, if you are not comfortable working with electricity, consult a qualified electrician. Let's consider some potential issues that might arise during motor installation or replacement. One potential issue is incorrect wiring. Ensure that all wires are connected to the correct terminals according to the motor's wiring diagram and the equipment's wiring diagram. Incorrect wiring can lead to motor damage or malfunction. Another potential issue is capacitor failure. Capacitors can fail over time, leading to starting problems or reduced motor performance. If you suspect a capacitor failure, test the capacitor using a multimeter or a capacitor tester. Replace the capacitor if it is found to be faulty. Another potential issue is overload. Overloading a motor can cause it to overheat and fail. Ensure that the motor is not overloaded and that it is properly sized for the application. Another potential issue is voltage fluctuations. Voltage fluctuations can damage the motor or reduce its performance. Ensure that the voltage supply to the motor is stable and within the motor's voltage rating. Motor protection devices, such as circuit breakers and fuses, are essential for protecting motors from overcurrent and short circuits. Ensure that the motor protection devices are properly sized and installed according to the electrical codes and regulations. Regularly inspect motors for signs of wear and tear, such as cracked insulation, loose connections, or unusual noises. Address any issues promptly to prevent further damage and ensure the motor's longevity. Motor maintenance, such as lubrication and cleaning, can also extend the motor's lifespan and improve its performance. Follow the manufacturer's recommendations for motor maintenance. Consider the impact of ambient temperature on motor performance. High ambient temperatures can reduce the motor's efficiency and lifespan. Ensure that the motor is properly ventilated to prevent overheating. When selecting a replacement motor, consider energy efficiency. Energy-efficient motors can save energy and reduce operating costs. Look for motors with high efficiency ratings, such as neoprene efficiency. Consider using variable frequency drives, also known as variable frequency drives, to control the speed of motors. Variable frequency drives can improve energy efficiency and provide precise speed control. Variable frequency drives adjust the frequency of the electrical power supplied to the motor, which in turn controls the motor's speed. This allows the motor to operate at its optimal efficiency point for varying load conditions. Here are some advantages of using variable frequency drives. Firstly, energy savings, as variable frequency drives can significantly reduce energy consumption by adjusting the motor's speed to match the load requirements. Secondly, precise speed control, as variable frequency drives provide precise control over the motor's speed, allowing for fine-tuning of the process. Thirdly, reduce mechanical stress, as variable frequency drives can reduce the stress on mechanical components by providing smoother starts and stops. Fourthly, extended motor life, as variable frequency drives can extend the motor's lifespan by reducing the stress in the motor. Fifthly, improved power factor, as variable frequency drives can improve the power factor of the electrical system. Variable frequency drives are commonly used in applications such as pumps, fans, and conveyors. They are a cost-effective way to improve energy efficiency and control motor speed. When installing a variable frequency drives, it is important to follow the manufacturer's instructions carefully. Variable frequency drives can generate harmonic currents, which can interfere with other electrical equipment. It is important to mitigate harmonic currents by using appropriate filtering techniques. Motor bearings are a critical component of motors. They support the rotor and allow it to rotate smoothly. Motor bearings can fail over time due to wear and tear, contamination, or improper lubrication. Regularly inspect motor bearings for signs of wear and tear, such as unusual noises or vibrations. Lubricate motor bearings according to the manufacturer's recommendations. Use the correct type of lubricant and avoid over-lubrication. If motor bearings fail, replace them promptly to prevent further damage to the motor. There are several types of motor bearings, including ball bearings, roller bearings, and sleeve bearings. Each type of bearing has its own advantages and disadvantages. Ball bearings are commonly used in motors due to their low friction and high speed capabilities. Roller bearings are used in applications that require high load carrying capacity. Sleeve bearings are used in applications that require quiet operation. Motor insulation is another critical component of motors. It prevents electrical current from flowing between the motor windings and the motor frame. Motor insulation can fail over time due to heat, moisture, or contamination. Regularly inspect motor insulation for signs of damage, such as cracks or discoloration. Test motor insulation using a megameter to ensure that it is within acceptable limits. If motor insulation fails, rewind the motor or replace it. There are several types of motor insulation, including varnish, epoxy, and mica. Each type of insulation has its own advantages and disadvantages. Varnish is a common type of motor insulation that is relatively inexpensive. Epoxy is a more durable type of motor insulation that provides better protection against moisture and contamination. Mica is a high-temperature type of motor insulation that is used in motors that operate at high temperatures. Motor cooling is essential for preventing motors from overheating. Motors generate heat due to electrical losses and friction. If the heat is not dissipated effectively, the motor can overheat and fail. There are several methods of motor cooling, including air cooling, liquid cooling, and forced air cooling. Air cooling is the most common method of motor cooling. It relies on natural convection to dissipate heat from the motor. Liquid cooling is used in applications that require more effective cooling. It involves circulating a liquid coolant through the motor to remove heat. Forced air cooling uses a fan to blow air over the motor to remove heat. Choose the appropriate method of motor cooling based on the motor's size, operating conditions, and application requirements. Ensure that the motor is properly ventilated to prevent overheating. Keep the motor clean and free of debris to allow for proper airflow. The NEC, or National Electrical Code, provides guidelines for the safe installation and wiring of electrical equipment, including motors. It is important to follow the NEC when installing or replacing motors to ensure safety and compliance. The NEC covers various aspects of motor installation, including wire sizing, overcurrent protection, grounding, and disconnecting means. Consult the NEC for specific requirements related to motor installation. For example, NEC Table 430.52 provides guidance on selecting the appropriate overcurrent protection for motors. NEC Section 430.12 provides requirements for motor disconnecting means. NEC Section 430.22 provides requirements for motor conductor sizing. The American National Standards Institute, or ANSI, develops standards for various aspects of electrical equipment, including motors. ANSI standards provide guidelines for motor design, testing, and performance. ANSI standards can be used to ensure that motors meet certain performance and safety requirements. The National Electrical Manufacturers Association, or NEMA, is a trade association that represents electrical equipment manufacturers. NEMA develops standards for electrical equipment, including motors. NEMA standards provide guidelines for motor dimensions, performance, and testing. NEMA standards can be used to ensure that motors are interchangeable and meet certain performance requirements. In conclusion, understanding motor wiring configurations, especially in capacitor start motors, is crucial for proper installation, operation, and troubleshooting. By following the recommended wiring practices, using the correct components, and adhering to safety precautions, you can ensure the reliable and efficient operation of your HVAC system.